Hey Justin,
Yeah.
I was curious. So looking at my calendar screen for lecture participation, and it's gone 0 out of 1.
Yeah.
So I was curious if mine account go to the.
Did you check that you're responding as student ID?
I think so. Yeah. So I was responding to this.
And so if you are certain about that, message me private post on Piazza, or the other thing, email works too.
Okay.
With your student ID, and I'll look and see what's going on.
Okay.
But before to just check that you are responding.
Yeah.
And then the other thing is, do tell me, like, I was there that day and that changes.
Thank you.
You're really from San Diego. Hold on. Try going somewhere else.
It looked like the second lesson. Like one show, yeah, I don't feel it. It tells you how to, like, gives you. Zero.
Okay, so I have 9:30 and we can get started. Today is Wednesday. So you have lab today, yes? And you are doing lab 1, right? You did lab 0 before. So lab 1, how many of you have read the lab documents? Okay, I want to, if Mark asked this question at the beginning of the lab time, I want to see all of your hands raised, okay? So do take a look at the lab document before you go to the lab. The lab is all about the different styles of modeling in VHDL. So behavioral modeling, architectural, which is structural, and then the data flow modeling and mixed modeling, right? So it's everything that we covered on Friday, right? Okay, the other thing is I posted lecture participation from last week. And when I reviewed the responses, some of you are still responding as not your student ID. So make sure you are responding as your student ID. And if that is the case for the previous week and you see 0, you were here, just private post on Piazza. So I have a reference of like I need to do this, and I'll respond back on Piazza when I have fixed it. And you can double check after I respond back. Email also works. I prefer Piazza. And homework 1 was posted. You guys got this notification from Piazza? Anyone not get the notification from Piazza? Okay. I don't think there's anything else, right? One thing I did forget is we didn't quite finish the lecture slides from last time, so I'm sharing the wrong slides. So I need to open up the correct slides. So lecture 3. Let's present this one. We need this slide. A share window. Oh, the other thing is I did post a link to all of the lecture recordings, also on Piazza. I'm uploading them to YouTube this time. I used to upload them to Google Drive, but in order to really watch the videos, you need to download them first. The video player in Google Drive is very bad. So, all right. So good practice. And we were talking about test benches. So what do we think are some good practices to follow when making test benches? Just any ideas. Like it doesn't have to. Oh, that's freaking. No one tell me. You guys can yell at me. Good practice. Okay, so yes.
Do you want to try to catch like a range of like testing so
Mhm.
that you can get all cases?
So wide range of test cases. Right? So if you're testing something very simple, like you're just making an AND gate, and it's a 2-bit AND gate, how many test cases do you have? 4 valid test cases, right? So in that case, this wide range of test cases, if it's simple, so if simple, test all, right? It's very simple to create those 4 test cases, and you can also create the other test cases of floating or multiple drivers coming in, and it would be a total of test cases under 100, right? It's going to be something like 16. So when it's yes.
Are there like try catch functions in VHDL?
So you can do try catch as C code in the test bench, but you wouldn't really need that for the simple models that we are doing. So to create a test case for VHDL, right, we're just changing the input, putting a wait statement, and then looking at the output during that time. The try catch is something that is used and can be very helpful for more complex projects. So that would be helpful, for example, with the memory lab as well as the final project. And the reason it's for both of them is because really the memory lab is the first part of the final project. Okay. So what else do you think is good practice? Let me ask you this question. Is this easy to read? So what else do you think you could do? Oh, yeah, they're labeled. It's just split up into 2 screenshots.
Yeah.
So like this is labeled, right? So I want to try and simplify it further than that. So I don't want to look at waveforms at all. Okay. So another thing that you can do is automate. So like try catch, you can do assert. So I know based on this input what my output should be. I can assert that they're equal, like what the expected output is compared to what the unit under test is outputting, and then just print out test passed if it's equal, right? And then I would just have to look at the console and scroll through and see if there's any fail. And I can make it even simpler by not printing every single test, but only print out fail if there's a failed test, and then pass all if all the tests are passed. Yep.
Would that be like, would you put in like a fail message for each input?
Yeah, so it would be the input, you wait, and then here you would check. So then you change the input, you wait, there's another check here. And this check is written very similar to C code. So you can, like I said, assert works. You can if statements. You can also just do that. If this is, you can do for loops. So you don't have to look at the waveform. For the first few times, and to get used to looking at the waveform, it might be helpful to force yourself to look at the waveform, because when you're debugging, you got to look at the waveform. There's no way around it. Well, there is, but you should have the skill of being able to read the waveform. Okay. So we want to automate. What else do we want to do? Any ideas? I'd say for most of your projects, this is sufficient. Okay. You want a wide range of test cases. So you want to cover all of your edge cases, especially if you have an infinite amount of inputs. You're not going to be able to test them all. But if it is simple, do just test them all. And then you want to automate so that you can just look at one message, see if it passed or if it failed. And the other thing I will mention, because it will be important later on, test all entities individually. So when you're creating a more complex project that is involving multiple entities, test all of the lower level ones on their own before you move on to utilizing them in a larger entity with a hierarchical structure design. Okay. So I think those are decent, good practice, and they should help you get through the labs in this course. And you can always get better at this if VHDL or HDLs in general are something that you do in, say, your employment. You will obviously get better as you work with it more. Okay. So we are reviewing combinational logic still, right? And your reading was on two-level logic minimization, right? So before on Wednesday, we talked about product of sum of products, and how to make that two-level logic unoptimized way, the very simple way. But now we're moving on to optimized. How can we get the two-level logic equation for this function that is the smallest circuit that we can have? So your reading question was on K-map, right? So here we can draw this K-map. So we have 1, 2, 3 inputs. So I'm going to put A, B here, and C here. All right. So C, when it's up here, 0, down here 1, right? AB, 0, 0, 0, 1. What goes here?
1, 1.
1, 1, right? 1, 0. Because we have to be careful when we're drawing the K-map, it's very common to put 1, 0 here. Between any two boxes, there should only be one bit flipped, right? So that's why we go from 1, 0, 1 to 1, 1, and then from 1, 1 to 1, 0. So this represents 0. This represents 1. This is 2. This is 3. This is 6, 7, 4, 5. Right? So we can just go to our truth table. So 0, 0, 0. This is 0. 1 is 0. 2 is 0. 3 is 1. And then 4. So this is 4, 5, 6. 4 is 0. And the rest are 1. Right? And then my next step here is to do what? Yes. So we need to circle the largest groups of, it could either be ones or zeros. It depends if I want to work with sum of products or product of sum. So let's just work with the ones in this case as an example, because that's my preference. But again, you don't have to follow any preference. But I'm going to do them in different colors. So here, they're next to each other. There's 2 of them. It's a multiple of 2, right? And it is the one of the largest circles I can draw. And now what I have to figure out is, what is this implicant that represents this circle? So what I need to figure out of what is going to be removed is the variable that's changing. Because the variable changes, the output does not. So the output does not depend on that variable, right? So it does not need to be in the equation. So what's changing across here? C. And then the 2 that are the same are A and B. And what are my values of A and B? So it's A and B for the green. All right, now let's do this one. So for the blue one, what's changing? So A is changing, and what's staying the same? And they're both ones, so it's BC. And then my last one is over here. So what's changing? And it's just AC, right? C stays one, A stays one. So we see how to draw these circles, how to get these implicants. Okay. So I want to talk a little bit about these implicants. So any one of these boxes, I would be able to circle, right? So 1 is a power of 2. It's 2 to the power of 0, right? And those would be our same thing from what we learned last time. We have A, B, where is this? All right, yeah, let's do it that way. So we have A naught, BC. We have, what's this one? A, B naught, C. And we have A, B, C naught, and then A, B, C, right? So these are just implicants. It's any circle that you can draw on the K-map. But the next thing that we had are the largest circles that we can draw. So we had from our previous one, AB, was it BC? Yes. And then purple was AC. So these are prime implicants. They're just the largest circles that you can draw, right? And then there's another class above these, which actually all of these are. I need to zoom out. Okay. So the class above these are prime implicants. So essential prime implicants are the largest circles that you absolutely need to include in your final equation in order to have the minimal equation. Yes.
Why would
A naught, B naught, C naught. So it's a implicant if you're circling zero.
Oh.
So the same thing is applied to the opposite. But in that case, it would be A, B. So A or B or C is the implicant for the product of some. And like I mentioned, all of these are actually, they're prime implicants and they're all essential prime implicants, because if I exclude any one of them, I don't get my full coverage. And my full coverage is having all of the ones circled, right? So are we clear on what's an implicant, what's a prime implicant, what's an essential prime implicant? Yes.
So you can have prime implicants without reaching the essential implicants, or by finding prime, you also find the essential.
So all of your essential primes will be primes.
But not all primes are essential.
Yes. So sometimes you'll have a choice of I can do this circle or this circle, but I
Uh,
have the same coverage. Okay. But in that case, yes.
Would an example of what you just said be if you had all 4 ones at the bottom, and then you did like a circle, and you did like a circle like that. That small circle wouldn't be one. The essential farms, because it already has the coverage with like the 4 at the bottom.
So
With that far left bottom one.
let's, where can we do this? It's not a good line. Here, 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 here. Let's do this. So you have this one. This is essential prime implicants. Well, actually, this example is not good either. Well, actually, no, yeah, it's not good either, because the other one is this circle.
What if you just did like a
Because this is actually larger than the other circle. The other circle is just one variable. This circle is 2 variables. I think it's only going to be really complicated when you have 4. I'm struggling to find a example where you have
If one of those
too
lone,
many
if
choices.
one of those lone ones was like to the left instead with that. You had a 1, 0, so it's
Yeah, but the only way that you're getting this is like this.
instead of another way.
Yeah, and then the only way you're getting this one is like this. There's no other way.
So there has to be multiple choices of
Yeah, so there has to be multiple choices. But the good thing is when you have multiple choices, you just have to make sure that you pick one of them. You don't pick them both.
So just to summarize, you can have prime implicates without getting essential prime implicates if you have multiple ways to write the circuit when you reduce it. Like if you had like 2 or
So
3 different ways to.
you can have, so essential prime implicants are always prime implicants. And when you have no coverage, but you have all of the, you haven't have full coverage, but you have all of the essential ones, then you're basically picking between the prime ones, which one I'm going to circle to get the last bits of coverage. Make sense? Okay. So question 2, we're talking about timing. So we have these gates and their characteristics. And what we want to figure out are 2 things. What is the propagation delay of a circuit and the contamination delay of a circuit? So propagation delay is the longest time between a change in the inputs to the final change in the stable output. Contamination delay is the shortest time between change in the inputs and change in the outputs. So when we're trying to find the propagation delay of this circuit, we need to figure out, based on the propagation delay of all of the components, what is my longest path? So in this case, all of my paths go through the same 2 gates, right? No matter what path I take, it's the XOR gates, right? 2 XOR gates that I go through. So my propagation delay for this circuit is 45 picoseconds plus 45 picoseconds, which is 90 picoseconds. Does this make sense? Okay. And then contamination delay is the shortest path between inputs and outputs based on the contamination delay timings. But again, all of my 4 paths are all the same. So the shortest is just pick any one of them, and all of them go through 2 XOR gates. So it's 29 picoseconds plus 29 picoseconds, 58 picoseconds. Right? So, do we have any questions on what propagation delay is? What contamination delay is? Okay, so propagation delay is the longest time between change in inputs to stable outputs. Yeah. Because your output will change, but in order to be considered a 1, it has to be more than like maybe 70% charged, right? And then contamination delay is the minimum time between change in inputs, change in output. Okay,
These timings just inherent in the gate.
yeah, so like it would be a characteristic of the gates that you're given. And it would change based on the size, like the sizing of the gates.
The kind of inputs and
So inputs as well as just the technology node.
oh,
So like 70 nanometer is going to be larger and take longer to charge than 10 nanometer. So it's just a characteristic of the gates. Okay, so now that you know the definition of propagation, contamination, this is your first question. So let me just make sure that it's active. So poll everywhere is active. The code is 533. Try and do this question on your own first. And the question is, what's the propagation delay? What's the contamination delay of the circuit? And when you're done, just answer anything to the poll. I just want it as an indicator of when you're done working on this. 533. Mhm. Mhm. What do you mean by resources?
Like, let's say, like maybe if you forget a gate or something, like what it looks like or any value.
You need to know what a gate is.
Okay, we need to know every single one of them. And we need to know all the equation forms and everything.
Some equations I will give you. But often, I mean, something like this, it's just find the minimum, find the maximum.
Mhm.
So I wouldn't give you that. But later on, you have a little bit more complicated equations with sequential logic timing. Those I give you guys.
Mhm.
But like if you ask me before the upcoming quiz, like what equations will I give you, I can answer.
Mhm. Okay, so if we had this one on like a quiz or something, you wouldn't give us the timing characteristics, or it depends what you're asking
Yeah,
for?
so the timing characteristics would be given
Okay,
because that's
I mean,
different. Yeah,
okay,
it's going to be different for every gate too. It depends on the sizing. So
Okay.
those would be given. You would need to know that you need to find the minimum and maximum path.
okay,
And you need to know that maximum is for propagation delay. Minimum is for contamination.
okay. Thank you.
Okay. I don't see anyone answering the survey yet. Yeah, so just answer anything when you're done. Yeah, I just am using it as an indicator of when are you done. So just answer anything when you're done. This is question 1. Question 2 is next. Okay, so maybe a better indicator right now is anyone still working on this? Okay. So let's go over this together. I'm gonna do propagation in red, contamination in blue. So propagation, what am I trying to find? The longest path, right? So most likely this path from C to Y is not my longest path, right? Because all paths are gonna go through this gate, right? Which is an XOR, which is 29 picoseconds, right? But all of these other paths above C have an inverter, an or an and then an or. So they're all, I don't even need to check C. I know for sure the paths A or B are going to be longer. Yes. Oh, yeah. It's 45. So we see that? I don't need to check C to Y. But the question is, for B, is an inverter plus an OR going to be greater than the other B or the A, which is a NAND or NOR? So we just need to check inverter versus NAND. So NOTS is 15, NAND is 30. So for sure, it's this path. And then the NOR is 25. So 25 plus 45, 70. And we're getting 100. So propagation delay is 100 picoseconds. Question? Because this is the path? Or this is the path? These are the same. Yes,
Okay, so it's about finding the slowest path
yes,
from any single input.
yes.
Okay, I was looking at like the whole circuit. Okay. That makes sense. I think,
This is the circuit as the
well,
whole.
I think the first example can kind of confuse me because they all went the same way anyways,
Yeah.
but this one, we're looking for the shortest or the longest path of one.
Okay, so it's more clear now then.
Yeah,
All right, so now contamination delay. So they're all gonna go through this. And this is actually 29 picoseconds this time, right? But then my paths above are again, now I'm going to include an inverter or a NOR, well, inverter and a NOR, or a NAND and a NOR. And we can just check the NOR. The NOR is 7, inverter is 5. I don't need to check all of these above paths. I just know that 5 picoseconds is going to be the longest path by visual inspection, right? Well, yeah, shortest, sorry. Right? So it's just 34 picoseconds is contamination delay. Make sense? Right. So we have one more. And this is question 2. So answer question 2 just when you're done individually working on this.
it's better to work backwards.
It just depends.
Oh,
In this case, because they all go through this one, I can basically just ignore that one, right? So that's why I was doing it.
okay.
But that's not always the case because you can have multiple outputs. And when you are done individually, you can just go ahead and complete the survey. You don't need to resubmit your answer because there's really nothing to resubmit it to. Okay. I think most of you guys are done. So let's do propagation delay first again. So what can we immediately just not look at? E to Y, right? Everything goes through Y. E has nothing before Y. And everything above it has something else. And then we can also look at the path from CD through Y compared to AB through Y. And we can see that they all include 2 AND gates, right? So all of this is all going to be the same. And I can even include Y there. The only difference between these is A and B go through another AND gates, whereas C goes through either an inverter or nothing additional, right? So we just need to compare the inverter to the AND gates, and we can see 15 versus 40. So 40 is going to be longer. So our longest path is 40, 40, 40, and this is an OR gate, 35. So 120 plus 35 is, right? And then contamination delay is pretty simple too. Again, they all are going to go through Y, which is a OR gate. So it's 10. And E has nothing else. Everything else above it has something else. Right? So for sure, the shortest one is E to Y. So contamination delay is 10 picoseconds. Are we all good with combinational logic timing? What is propagation delay? What is contamination delay? How to find it given a digital logic circuit? And of course, the timing characteristics. Okay. And we are all also good with K-maps. We did this 3 inputs as an example. I think your homework has 4 inputs. So just being able to do those, we're all good. All right. So again, look at lab 1 before you go to CMARC. And check Canvas for your participation. If there's a problem, let me know.
What is it called? Contamination? Are we worried about our output doing that stuff on something or?
Yeah, so it's really called contamination delay because of sequential logic timing. Because the reason is if the contamination delay is too short, then before you're stable on the register, it can contaminate the previous result.
Okay.
So that's why it's called contamination delay.
Yeah, well, yeah, we start talking.